G'day guys, welcome to video 2 of topic 2 of unit 4, intensity. Alright, so here are our learning intentions and our success criteria. We'll be covering the main ideas of chapter 16.3 of book 1. Okay, not book 2, book 1. Please do that reading. So here are your learning intentions and success criteria. Please have a read, pause the video and attempt to complete the KS table there over on the right. Okay, so we can see here, what you want to be able to do is define intensity and use the inverse square proportionality with distance to make calculations. So 2 success criteria: define it first and then calculate based off this inverse squared proportionality. So in terms of knowledge, we need to know, well, what is intensity? If we don't know what it is, we can't really define it. And the second thing is, well, if we're going to calculate based on this idea of inverse squared proportionality, well, we've got to know what that is first, and then once we know what it is, we can do that thing and calculate with it. So let's talk about intensity first. Hold your hand in front of a fire or a heater. It's pretty cold at the moment, so you might have the heater out in the morning. Perhaps you can feel the electromagnetic radiation, maybe you can't. Okay? If it's too hot, you move back away from it. If it's not hot enough, you go closer to it. And what you're feeling there is intensity. One way I think of it is intensity is the concentration of energy, sound or light, at some location. Okay. Here's the text definition: the average flow rate of energy per area. Okay. Now, well, what about time? Let's think about time for a second here, because we've got the energy, we've got the area, but where's the time? It's coming out of that word flow rate. But let's understand what we mean by this. What would hurt more, holding your hand a few centimeters from a candle flame for a few minutes, or flicking your hand quickly through a yellow Bunsen? Okay, now, I'm sure you've probably done the Bunsen flick. I know I did it in high school. But holding my hand right over a candle a couple centimeters above the flame, a candle's pretty small, but that flame, puts off a little bit of heat, and if you're there for a while, that will hurt you. Okay, so don't do that. So there are 3 things we're going to think about here: the total energy, the distance from the source, and how quickly the energy arrives. So let's start with power, because that's going to talk about our flow rate of energy. Power equation is power equals energy divided by time, and Walding often uses power equals work divided by time, because remember, work is energy that is being done to something. So if you heat something up, you could say the sun is working on you while you stand out in it and heating you up. That energy is doing something. Now, waves are energy that's transmitted. Okay, it is the transmission or the movement of energy, and so that means they have to have a power. If it's an energy, okay, and we can deliver the energy from one place to another in a given time, there must be power. So light, sound, they have power. Okay? Now, the other big variable that we saw in our definition was area. I want you to think of a magnifying glass. Okay? Now, if you stand out in the sun, things get hot. Okay? Sometimes it can be nice, like at the moment, it's a bit chilly. You can stand out in the sun, get a little bit warm, feel good. Give us a few months, we'll all be cursing the sun because we'll be back to being summer again, and summer in Queensland is hot. So, but if we take a magnifying glass and we put it in the way, it doesn't matter if it's winter, doesn't matter if it's summer, that will start burning you fairly quickly. Okay, you put in skin, you put in paper, that's going to hurt. Now, the power on our magnifying glass here must be the same. The power in must equal the power out, because power is just energy per time. We're not changing time here. We're not applying any sort of weird special relativity or general relativity to mess with time dilation. We haven't changed the amount of energy from the sun. All we're doing is we're changing the direction that the energy goes. Okay? So the power in must equal the power out. But what we know is that up here on top of the magnifying glass, you can put your hand there, feel okay. If it's summer, it might get a bit warm, but it's not going to burn you. So it's low intensity. The area is bigger though. But if we put our hand down here at the bottom, well, the area is a lot smaller. I mean, look at the size of the black dot there compared to the size of the magnifying glass. It's a lot smaller. Yet, the intensity is a lot higher because it can burn us. Okay? So therefore, intensity must be connected inversely to area. Now, Walding derives the following formula, and we're going to look at this for a second. Here's the formula for power, okay? And we have this idea that average flow rate of energy per area. So power is flow rate, and we're going to divide it by A for area. Now the syllabus descriptor is to define intensity. There's the definition, and so we can see the power is the flow rate, okay, and it's being divided by the area, okay. This formula is not provided to you, okay, but if you understand the definition for intensity, it's not a particularly difficult one to construct. So I'd just be aware of that. The other thing, remember, is that intensity in the terms of the units, we'll see on the next page, is just the combination of these two units. So if you know that power is measured in watts, which you have to because that's a required part, and you know area standard unit is measured in meters squared, which you should by now, then you can go, oh, well, if intensity is watts per meter squared, and I have watts and I have meters squared, well, I just need to divide these two numbers. So remember, units can clue you in on what you have to do. I used to do that all the time with a wave equation because I can never remember which way to organize it. So here's the formula, here's a summary for it. I is intensity, as I said, in watts per meter squared. There are some other units of intensity like lux, but the conversions between lux and watts per meter squared is pretty tricky, and there's no mention of the unit lux anywhere in the syllabus, so we're going to keep it like this, which is why I don't think that this would be the sort of calculation questions on the exam. Define, yes. The example 16.3c we're going to do, yes, but 16.1 and 2, A and B, sorry, not as likely because we're not using the unit for intensity that we could use. So I have a feeling that perhaps they might not need you to do something like this, but it's worthwhile understanding it. So power's in watts. Remember our bad Harry Potter joke, get a unit of power, Harry, and then A for area in meters squared. So let's have a look at some examples. Oh, I forgot to cut off the solution on this one. So you can see the solution there. Calculate the intensity of a 100 watt beam of radiation over an area 4 meters squared. This one's really straightforward, so I probably don't need to show you anything. We have our formula, intensity equals power over area. We have our 100 watt, our power. We have our area given to us at 4 meters squared. We substitute, we solve, done. Okay, so that one's pretty, yeah, let's go on to 16b. A can containing 100 ml of water is placed near a high intensity floodlight. The area of the can exposed to the light is 8 centimeters by 15 centimeters, and the energy delivered to the can was 1,428 joules in 5 minutes. We're asked what is the power, and then what is the intensity of the radiation at the surface, assuming that it's all thermal energy. So it's assuming that all the intensity is going into thermal energy. This sort of situation here, like, I'd kind of be nice if intensity, like the formula for this, was on the formula booklet, because this would then connect really well into our heat studies, and you could work out intensity in terms of converting into heat. Unfortunately, it's not. So let's chuck that out of the way. Load up the question on my computer so I can see what I'm working with. Alright, so we have a couple of things. The 100 ml of water at the start, that's a distractor. Okay, we don't need that number. It's not useful for anything. None of the formulas we've seen so far to this video have anything to do with volume, okay, or mass. Okay, when you think of volume, also remember that especially for water, volume and mass are interchangeable here. 100 mils, 100 grams. But nothing we've seen has used mass. So let's not worry about it. We are told an area, okay, and the area equals 8 centimeters. I'm going to convert straight away to meters, times 15 times 10 to the negative 2 meters. Okay, I would always recommend, as soon as you see centimeters converted to meters, it's so much easier than dealing with centimeter squared to meter squared. And if we chuck that into the calculator, let's grab said calculator. Oh, let's see, 8 times 10 would be 80. 8 times 5 would be 40, so together that would be 120. 8 times 15 times 10 to the power of negative 4, 0.012. 0.012 meters. Okay, and we are told that there is some energy. We have an energy of 1428 joules, and we're told the time it takes is 5 minutes. So let's convert that into seconds. 5 times 60 will be 300 seconds. Okay, so now we've got our two formulas. Well, part A is asking us to work out the power, so let's just work through that way. A, we want to know the power. Power equals energy divided by time. 1428 divided by 300 equals 4.8 watts. Let's see, 3 into 15 would be 5, so that seems reasonable. It has been rounded off, 2 sig figures, because all our numbers, we're told it's 8.0 centimeters, and we're told it's 5.0 minutes. So yeah, 2 sig figs. Now part B here is after what is the intensity. We know that intensity equals power divided by area. We know power, we just worked it out before, 4.8, and we know that our area is 0.012, which should give us 400 watts per meter squared. Okay, pretty straightforward, but as I said, I don't know if this formula would actually appear, or these sort of questions would appear in the final, but it's worthwhile using this to help us understand what intensity means. How's that lined up? Okay, so we haven't talked about distance yet, because what we've looked at so far is defining the idea of intensity and having a formula that falls out of that definition. As we said at the start, you move further away from a source, you move further away from your heater, the intensity of the radiation or the intensity of the energy being delivered to you gets less. Okay? So it must be proportional or inversely proportional to distance or radius. But the question is, we've got two of these. Is it inverse or is it inverse squared? Now, if you remember the success criteria, you're probably going, well, it's inverse squared. But how do we know it's inverse squared? Now, think about an object. My fist. Hang on. Where's my camera? My fist. A distance equidistant from the center of my fist, okay, would be a sphere. Very hard to draw a sphere in 3D on a camera. So imagine a handball in front of you. If you go an equidistant away from the surface, you get another sphere. A ball is a sphere. If you go away, you get another sphere. Okay. Well, we just saw that it all had to do with area. The area for a sphere is 4 pi r squared. So if we substitute that, the 4 pi is just a constant, that doesn't matter in this case, but the r squared is the thing that's changing. So that tells us it must be proportional to 1 over r squared. Okay, so this formula, that's what's provided, this one here, which is new. This is, I think, and I may be wrong, but I'm pretty certain this is the only formula in the entirety of the textbook that uses a proportionality rather than an equals, which makes things a bit tricky. We'll talk about that in a second. Here's a way to understand the connection between area. We can see here at radius, area, at 2 times the radius, the amount of area is now 4 times. At 3 times, it's 9. So 1 to 4, or so 1, 4, and 9, that's a square power sequence, so we can see it's going up proportional to r squared. 1, 2, 2 squared, 3, 3 squared. Okay? But remember, the formula is given to you on the formula booklet. Now, proportion equations. This is something new for us. You can try to logically think your way through these, and I mean, that's perfectly fine. I think I did a fair number of those back in high school when I was doing my end of year exams. I know that I did that for Half-Life during my QCS exam, where it was something like that, and I couldn't do the equation off the top of my head, so I just had to reason it out, going, okay, well, Half-Life means there's half, let's work out how many Half-Lives, and just chunking it out step by step. So this is what I would call, if we think about this, if I is proportional to 1 over r squared, then I must equal k over r squared. What k is, I don't know. It doesn't matter. Okay? But what we do know is that the k will be the same no matter what situation we're in. Okay? So if I rearrange this and I bring r squared to the other side, I now have that I times r squared equals k, and that's true for any other situation. So if we think about a light here, okay, and we're some distance from it, I times r squared will equal a number. As we go over to here, I times r squared will equal the same number. And so we can set up this, think of it like a before and after equation, okay? When this is true, this proportionality is true, okay? If it was 1 over r, then it'd just be I times r equals I times r. But because it's r squared, it's I times r squared equals I times r squared. So the 1 for initial, 2 for final, we could have used I and F if we wanted to. This is not provided in your textbook, and I'd recommend spending just a little bit of time making sure that you can understand why this is true, so that if you are working with proportionality or intensity type questions, you can quickly get to this. It will save you time. Okay, so this is a before and after. There's also a way to think about it in terms of ratios, but note, I think this one might be a bit tricky in that, I1 over I2, yeah, cool, equals R2 squared over R1 squared, because the proportionality is inverted or inverse. So here our r's have to flip over each other. Realistically, this is saying 1 over r1 squared over 1 over r2 squared, which if you simplify the fraction of a fraction divided by a fraction, you end up with this. Okay, so math aside, you're going to have to use one of them. So I would recommend picking whichever one that stands out to you and sticking with that, because you can see that this and these two things here, they're just rearrangements of each other. Okay, this one here, I take my r1 squared to this side, take my i2 to this side, I get that one. So you choose. So let's have a look at our next example. Street lights in figure 2, yeah, I didn't bother putting the picture in, are all 500 watt sodium vapor lamps. There's our power, 500 watts. A student is standing 20 meters from the first light. Assuming no absorption or scattering of light, what is the intensity as measured from the student's position? And where would the student have to stand to measure that intensity as half of this? Okay, so let's think about this question for a second. Imagine you are standing, and I will get my pen out and draw some really bad drawings. Okay, how do I draw a lamp? Here's a lamp. Not a good lamp, but it's a lamp. And here's my person. Now they are 20 meters away from it. Radius equals 20 meters. Okay, so think about that. That radius, that's a big sphere around our center here. Okay, and we know the area for a sphere. I saw it on a slide there a second ago, 4 pi r squared. Okay, so that 500 watts, this thing here has a power of 500 watts. At this whole distance, that also has a power of 500 watts, but the area is a lot bigger now. Okay, so once we know the area at that point, we can work out the intensity at that point. Here, the radius might be something like 20 centimeters, 0.2 meters. Okay, normally when you've got a light bulb, it's talking about, well, how much joules of energy per second it's drawing. It's not telling you what the light intensity is at the surface of the light. Though information probably is on the box, but I've never really looked for it. I've always looked for wattage. So let's work out the area here. I'm going to put the whole formula. I equals P over A. I equals 500 for the power divided by 4 pi. Instead of R, I'm going to write 20 squared. And if we chuck all in of those, we get that the intensity at this point is 0.10 watts per square meter. Okay, oh, sorry, that's part A. Pretty straightforward, but we just have to clue in there that it is a thing. Now, what you're more likely to see in questions like, at a distance of 20 meters, the intensity is equal to 0.1. How far would you have to be, and this is the part B, for the intensity to be half that? I have a feeling that the information like this provided is not as likely to happen. But it's worth understanding the formula as a just in case. So let's think about situation 2. We have that I1 equals 0.10, and we have that R1 equals 20. We want to know what's R2 for I2 to be equal to half of I1. So if we read what the question says, where would the student have to stand, that's our radius, to measure the intensity as half of this? So we need to know, well, how far we're going to be for this to be half. If this was a multiple choice question, I would expect a distractor of saying, oh yeah, 40 meters, because you go, intensity's half, radius doubled. But radius doesn't double. Remember, radius is proportional to square, okay? And it won't be equal to something like 160 meters, so as in doubling it and then squaring it. It'll be something else. So that means that should equal to 0.05. Now we can take our proportionality that we did before. So I1 over I2 equals R2 squared over R1 squared. Let's do this one, or we can go I1 R1 squared equals I2 R2 squared. Either or, doesn't matter which you start with, because remember, that's just a rearrangement of that. And since I don't know R2, I'm just going to use this one over here. So 0.1 times 20 squared equals 0.05 times R2 squared. So we can divide that over. 0.1 divided by 0.05 would equal 2. 20 squared should equal 400. So 2 times 400 equals R2 squared. So R2 will equal the square root of 800, which I believe, according to the thing, is 28. Probably a bit of rounding there. Double check. Yep. Okay, so the intensity stuff can be a little bit trickier because, you know, we're given only I is proportional to 1 over R squared. You're going to need to memorize one of these. It doesn't matter which, but it is going to be kind of important, so that if you do get a question on intensity, you are able to work it out reasonably well. Okay? If you find that it's your hard thing, what I'd recommend you do is just skip intensity questions and then come back to it after your brain's processed it a little bit, and try it in the last couple of minutes. So, in this lesson, we've gone through the following. What is intensity in terms of energy per area? We've calculated intensity using that definition, which again, I don't think would be, but perhaps. And then finally, calculate intensity using an inverse proportionality equation. For your entrance slip to class, please complete questions 1 to 7 in chapter 16.3 and copy your answers into the 4.2.2 space on eLearn. Thanks for listening, guys. Have a great night. Bye.